Hello students, so today we are going to discuss about the chapter 5 of microprocessor and microcontroller, that is 8086 microprocessor. So in this chapter, first of all we will discuss about the register organization of 8086. The 8086 has 4 groups of the user accessible internal registers. These are instruction pointer IP, 4 general purpose register AX, BX, CX and DX, 4 pointer register, that is stack pointer, base pointer, stack index and destination index register, 4 segment registers, that is CS, DS, SS and ES, 4 segment, data segment, stack segment and extra segment, then flag register FR. The 8086 has a total of 14 16-bit registers, including a 16-bit register called the status register, that is flag register, with 9 of bits implemented for status and control flags. Most of the registers contain data or instruction offset within 64 kilobyte memory segment. There are 4 different 64 kilobyte segments for instructions: stack, data and extra data. To specify where in 1 megabyte of processor addressable memory these 4 segments are located, the processor uses 4 segment registers. So next is segment registers. So first one is code segment. It is a 16-bit register containing address of 64 kilobyte segment with processor instruction. The processor uses code segment for all access to instructions referenced by the instruction pointer IP register. Then next one is stack segment. It is a 16-bit register containing address of 64 kilobyte segment with program stack. By default, the processor assumes that all the data referenced by the stack pointer SP and base pointer BP is located in the stack segment. So, stack segment register can be changed directly using pop instruction. So next one is data and extra segment. It is a 16-bit register containing address of 64 kilobyte segment with program data. By default, the processor assumes that all the data referenced by the general register, that is AX, BX, CX and DX, and index register SI and DI, is located in the data and extra segment. So next type of register is data register. So first one is AX, that is accumulator. It consists of two 8-bit registers AL and AH, which can be combined together and used as a 16-bit register AX. AL in this case contains the lower order byte of the word and AH contains the high order byte. Accumulator can be used for IO operations and string manipulation. So next is BX, that is base register. It consists of two 8-bit registers BL and BH, which can be combined together and used as a 16-bit register BX. BL in this case contains the lower order byte of the word and BH contains the high order byte. So BX register usually contains a offset for data segment. So next one is CX, that is count register. It consists of two 8-bit registers CL and CH, which can be combined together and used as a 16-bit register CX. So when combined, CL register contains the low order byte of the word and the CH contains the high order byte. Count register can be used in loop, shift or rotate instruction and as a counter in string manipulation. So 8086 has the loop instruction, which is used for counter purpose. When it is executed, CX of CL is automatically decremented by 1. So next one is DX, that is data register. It consists of two 8-bit registers DL and DH, which can be combined together and used as a 16-bit register DX. So when combined, DL register contains the low order byte of the word and DH contains the high order byte. DX can be used as a port number in IO operations. So in integer, 32-bit multiply and divide instruction, the DX register contains high order word of the initial or resulting number. So next one is pointer register. So first is stack pointer. Stack pointer is a 16-bit register is used to hold the offset address for stack segment. And base pointer is a 16-bit register is used to hold the offset address for stack segment. So the base pointer register is usually used for based index or register indirect addressing mode. The difference between stack pointer and base pointer is that the stack pointer is used internally to store the address in the case of interrupt and the call instruction. Then source index and destination index. This two 16-bit register is used to hold the offset address for DS and ES in case of string manipulation instruction. So SI is used for indexed, base index and register indirect addressing as well as a source data address in string manipulation instruction. DI is used for indexed, base index and register indirect addressing as well as a destination data address in string manipulation instructions. The next, instruction pointer. It is a 16-bit register. It acts as a program counter and is used to hold the offset address for code segment, that is CS. So next type of register is flag register. A flag is a 16-bit register containing 9 1-bit flags. So first is overflow flag. This flag is set if an overflow occurs, that is, if the result of a signed operation is large enough to be accommodated in a destination register. Next is direction flag. This is used by string manipulation instruction. If this flag bit is 0, the string is processed beginning from the lowest address to the highest address, that is auto-incrementing mode. Otherwise, the string is processed from the highest address towards the lowest address, that is auto-decrementing mode. The next one is interrupt enable flag. If this flag is set, the maskable interrupts are recognized by the CPU. Otherwise, they are ignored. Setting this bit enables maskable interrupts. Then single step flag. If this flag is set, the processor enters the single step execution mode. In other words, a trap interrupt is generated after execution of each instruction. The processor executes the current instruction and the control is transferred to the trap interrupt service routine. Next is sign flag. This flag is set when the result of any computation is negative. For sign computation, the sign flag equals the MSB of the result. Next is zero flag. It is set if the result is 0. Next one is auxiliary carry flag. So this flag is set if there was a carry from or borrow to bits 0 to 3 in the L register. Next, parity flag. This flag is set if parity, that is the number of 1 bits in the low order byte of the result, is even. So next one is carry flag. This flag is set when there is a carry out of MSB in case of addition or a borrow in case of subtraction. For example, when two numbers are added, a carry may be generated out of the most significant bit position. The carry flag in this case will be set to 1. In case no carry is generated, it will be 0. So next one is internal architecture of 8086 microprocessor. The 8086 has two parts, the bus interface unit BIU and the execution unit EU. The BIU fetches instruction, reads and writes data, and computes the 20-bit address. The execution unit decodes and executes the instruction using the 16-bit ALU. The two unit function independently. Then minimum and maximum mode. The minimum mode is selected by applying logic 1 to the MN by MX input pin. So this is a single microprocessor configuration. The maximum mode is selected by applying logic 0 to the MN or MX input gain. So this is a multi-microprocessors configuration. And this diagram shows the architecture of 8086 microprocessor. So the bus interface unit performs all the bus operations such as instruction fetching, reading, and writing operands for memory and calculating the address of the memory operands. The instruction bytes are transferred to the instruction queue. It provides a full 16-bit bidirectional data bus and 20-bit address bus. The bus interface unit is responsible for performing all external bus operations. So specifically it has the following functions: instruction fetch, instruction queuing, operand fetch and storage, address calculation, relocation and bus control. The bus interface unit uses a mechanism known as an instruction queue to implement a pipeline architecture. This queue permits the fetch of up to 6 bytes of instruction code. Whenever the queue of the base interface unit is not full and it has room for at least 2 more bytes, and at the same time execution unit is not requesting it to read or write operands from memory, the bus interface unit is free to look ahead in the program by perfecting the next sequential instruction. These prefetching instructions are held in its FIFO queue, that is fast in fast out, with its 16-bit data bus. The bus interface unit fetches 2 instruction bytes in a single memory cycle. After a byte is loaded at the input end of the queue, it automatically shifts off through the FIFO to the empty location nearest the output. The execution unit accesses the queue from the output end. It reads one instruction byte after the other from the output of the queue. If the queue is full and the execution unit is not requesting access to operand in memory. So these intervals of no bus activity which may occur between bus cycles are known as idle state. If the bus interface unit is already in the process of fetching an instruction, when the execution unit requests it to read or write operand from memory or input-output device. The bus interface unit first completes the instruction fetch bus cycle before initiating the operand read or write cycle. The bus interface unit also contains a dedicated adder which is used to generate the 20-bit physical address, that is output on the address bus. This address is formed by adding an appended 16-bit segment address and a 16-bit offset address. For example, the physical address of the next instruction to be fetched is formed by combining the current contents of the 4-segment register and the current content of the instruction pointer, that is IP register. The next one is execution unit. The execution unit is responsible for decoding and executing all instructions. The execution unit extracts instructions from the top of the queue in the bus interface unit, decodes them, generates operand if necessary, and passes them to the bus interface unit and requests it to perform the read or write bus cycle to memory or I/O device and perform the operations specified by the instruction on the operand. So during the execution of the instruction, the execution unit tests the status and control flags and update them based on the result of executing the instruction. If the queue is empty, the execution unit waits for the next instruction byte to be fetched and shifted to top of the queue. When the execution unit executes a branch or jump instruction, it transfers the control to a location corresponding to another set of sequential instructions. Whenever this happens, the bus interface unit automatically resets the queue and then begins to fetch instruction from this new location to refill the queue. This is all about the architecture of 8085. Thank you.